Hey, welcome back to Numerical Analysis. So I thought I'd get outside and record for a little bit. I just finished recording my intros for my tomography class, and so while I'm out here, I figured I'd keep things interesting, and I'll do one for numerical analysis. So you can see, this is my backyard, and we're right next to a nature preserve, so there's going to be quite a lot of noise. We actually get bobcats and other things from around here. I've seen deer out here a few times, bunny and raccoons. So I don't know, maybe we'll have a visitor here and there as we go. Mainly it just turns out to be loud birds, which is really annoying for recording. Anyway, we have thus far recorded up through doing lectures for it was Newton's method, I think, and I was going to get to more on the secant method and a few other things, and maybe if there's time, I'll go back and do that. But in the interest of time and considering the other things we want to cover, so for instance, I want to talk about gradient descent, which is what we're talking about today. But then there's a few other things like initial value problems and whatnot. And then I wanted to sort of tie everything together with a project that actually I have published that sort of integrates everything all at once. But today what we want to talk about is the sort of optimization method. So the topic of these couple of lectures for like Newton's method and doing things with and what we're going to do with gradient descent method is basically sort of things you do with nonlinear functions. So for Newton's method, basically the idea was that we wanted to find the roots of nonlinear functions, and we use that by taking derivatives and linearizations and following those to zero and using that as sort of the next guess. And we saw there are some, if you start in a small region of where the actual answer is going to be, then you'll converge there. The gradient descent method is something that takes a look at a different kind of idea, and this is for finding maximums and minimums, gradient descent is for finding minimums of a function. You can flip it around and find maximums if you want. But in order to do this in sort of its full practicality, we need to talk about functions of several variables. The gradient is simply the derivative of a function of several variables, and so we're going to be taking a look at it in this light. So if you remember back from Calculus 3, we had the gradient of, say, a two-dimensional or even a three-dimensional function. And if you look at the level sets of that function, the gradient ends up being the direction of maximum increase. So if you follow that, then you're going to be increasing the most infinitesimally in that region. And so then they actually sit as sort of being orthogonal to our level sets. Now, the gradient descent basically means that you're going to be decreasing in the you're going to go in the direction of maximum decrease. And so the idea there is that if we want to find the minimum of a function, well, we should start at a point and then just start decreasing as fast as we can. And so this has led to a whole collection of optimization routines that basically operate this way. So if you are given, say, a collection of something that's like a function that you want to decrease as much as you can, say you want to find the minimum energy, or you want to find sort of a best fit for like a polynomial, and this is related to our polynomial derivative, our polynomial approximation stuff that we did before, then the idea is that you want to follow, you want to take the gradient and you want to adjust your x from wherever you start to a point that you hope is going to be smaller by following the gradient down, the negative of the gradient. And so then you iterate this over and over again, just like with Newton's method, and then you hope that eventually you'll get at the smallest part. I'll go ahead and stop here, and then we can go ahead and we can talk about how all this works. All right, I'll see you on the other side. Okay, so what we're going to talk about today is sort of optimization. Optimization. And the gradient descent algorithm. Okay, so we know in general that if you have, say, a function of one variable, so f is going from, say, r to r, then there's something called the Fermat's theorem that tells you that if you have, let me move this microphone to a better spot. Let's see, yeah, there we go. So it tells you that if f attains a local maximum or minimum at a point, say x equals a, then f prime at a should be equal to 0. Right? I've always found it curious that this was called Fermat's theorem because honestly, Fermat was like maybe 50 years before calculus. Like he died roughly around like the birth of Newton-ish. So he didn't have a notation of f prime, but maybe there was some other way of interpreting this. I'll have to look it up someday. Any guess? So that's the general idea, and so what we're looking for in the gradient descent method is we're looking for these places where the derivative is 0. So I could have something like this, and we'd say start a guess just like with Newton's method. We'd say guess I think it should be here at x naught, and then you can say, well, clearly it's not 0 here. We have a slope like this, and then you say, okay, well, we'll follow the slope downwards, and so then we just keep following it, but we choose some sort of step size, etc., and then ultimately the idea is that we should converge and get to where we were hoping. So x2, etc. And so hopefully we can find, boom, this. But you see already there's a lot of uncertainty in this equation. So one thing we need to watch out for is what exactly we mean by moving a step, right? So how do we figure out something that we should call a step size? And how do we know we're going to find this minimum versus, say, this minimum? This function has two local minimums, and so how do we, rectify that? And so there's going to be two ideas, basically one big idea that we are going to run into, and we're going to be using convex functions. And so this is a function such that if you take f of x plus y, this is going to be less than or equal to f of x. Oh, sorry, it's a little bit. If you take x times lambda plus 1 minus lambda times y, then this is going to be less than or equal to lambda times f of x plus 1 minus lambda times y. And generally speaking, f of y. Here. That's what happens when I'm a little distracted. There we go. f of y. So basically, it says that if you have 2 points here, x and y, then a convex function basically stays underneath the secant line of those points. So this could be something like x squared or the exponential function, things like that. But it wouldn't be this guy, because we have these 2 points here and it stays above it, and so that's not convex. Actually, that would be concave. But in this region it's concave. But over here, I mean, we have both underneath and over the top of this line, and so those obviously aren't going to be convex or even concave functions. Okay, so then, all right, that's the start. So what about the step size? Well, the step size we're going to confront when we go ahead and take a look at proof of the gradient descent. And in this proof, we actually have to declare what the step size is going to be. And it's going to be some proportionality that involves, say, the derivative of the of the function, but we can get to that later. So let's get a little bit more precise about some of the things we're talking about. So first of all, we're going to be talking about a function f going from Rn to R. So up to now, we've just been sticking to just functions of a real variable, and we're making a change here to being a function of several variables, 2, 3, 4, etc. This gradient descent method is used a lot when you talk about things like coming out of data science, machine learning, and in those cases, the dimensionality could be thousands or millions, and so this algorithm has to be pretty general, and it's actually relatively simple. Okay, so we have this function f, and we want an algorithm that finds its local minima. Right, and in the case of some other functions, we want to have a guarantee that we're going to be converging to a point that is going to be a minimum value for f. Even convex functions can have multiple points that have minimum that minimize a function, but those end up being a very special sort of case. But yeah, so we want to have that, and so we need to ask what is a local minima. So we'll go ahead and start with a definition, and so we'll draw a little picture over here. It would say A, right? And we're going to put this little ball around it. So definition, a point x equals a, which is going to be Rn, of a function f going from Rn to R is called a local minima of f if say there exists a delta greater than 0, so this is going to be a radius, such that for all say y within delta of a, so say pick y here or pick y here, etc. We have f of a is going to be less than or equal to f of y. So everybody around it has to be bigger, at least in some local neighborhood. And you can also define a local maximum just by flipping this interval, this sign here. So we'll say a local maximum means f of a is going to be bigger than or equal to f of y in the same setting. Right. And it turns out, this theorem, if a is a local maximum, local minimum is a local minimum or maximum of f, or a local extrema, then the gradient of f at a is equal to 0. Okay, so then basically what we're going to be doing is just like in, say, Calculus 1, we're searching for the points where the gradient is going to be 0 or the derivative is equal to 0. The gradient is actually the derivative of a several variable function in a very real sense. And it turns out that if you take a vector valued several variable function and you take a look at its derivative, that actually ends up being a matrix. And so when you move from, say, derivatives to of single variable functions to multivariable functions, you start getting vectors or matrices, etc. And so in this case, we have that the derivative of a function of several variables is the gradient. And if you don't remember, so definition, the gradient of a function that is differentiable f over r to r is defined as this. And so it's going to be the gradient of f at x and I'm going to use angle brackets to represent a vector in this case. And we usually think of gradients as row vectors. Although some other people actually do think of them as column vectors, and so you just have to be careful about the notation when you're confronting a new paper. But so we have d by dx1 of f of x, comma d by dx2 f of x, and etc. And basically we just make a vector of the partial derivatives at this particular point. And there you go, and that's the gradient. Okay, so so generally speaking, what is the gradient descent method? And so this is going to be kind of a high-level overview, and then we'll have to go and dive into some particulars about a lot more things. So what is the gradient descent algorithm? All right, so so our goal is to find x equals a such that f, the gradient of f at a is equal to 0, right? And then we're going to take that as our local extrema and our local minima, and yeah, and then that's what we're going to be looking for. And so so we initialize our algorithm with a guess, say x naught, and say somewhere in Rn. Now, the general idea is that you have some level set that x naught is living on. So this is this collection of all y and Rn such that f of y is equal to f of x naught, right? And I'll just assume this is simply connected region. So if you take the gradient of f at this point, we know from, say, calculus 3 that it's going to be perpendicular to, say, a level curve or a level surface. And so so basically that's where you're going to get. And it's going to be, let's just say the minimum point is, say, here, fa. And so basically going outside of that, we're going to be getting bigger. So this is going to be, say, the gradient of f at x naught. Remember, the gradient points in the direction of greatest increase from the point where you took the gradient. And so if we want to get to the local minima as fast as possible, then what we need to do is we need to go in the opposite direction of that. And that's going to be the direction of greatest decrease. And so what we're going to do is we're going to follow this guy at negative gradient of f of x naught. And we're going to follow it to some point, and that point is going to be, say, x1. And then this is going to have its own level curve, and then we go ahead and we take the gradient here, and we just keep following it until we get to f of a, or at least in some acceptable region of f of a. And so that's what we're aiming for. Okay. So so then, like I said before, the step size is important. If we just choose a dramatically large step size in the beginning, you could jump right out of there and get even larger. And so you need to be careful about the step size that you take, and yeah, and then otherwise you just need to take the gradient and follow it down. So now we're not always going to end up in a case where we have a nice clean minima, and part of the reason that is that not all the functions are going to be convex. So generally speaking, when people are talking about convergence of gradient descent methods, they are generally assuming that they're working with a convex function. A lot of convex functions do come up in literature, and in fact, loss functions and other things that come up in data science and regression and things like that are designed to be convex so that we can take advantage of things like the gradient descent algorithm, and we have guarantees of minima. Linear functions are convex. They actually don't satisfy with the inequality, but with an equality. But there are a whole host of algorithms that you can use for linear functions, although gradient descent works there too. And I think, in fact, there's a method called a conjugate gradient descent, which works very, very quickly to solve linear systems. Okay, so let's go ahead and demonstrate a couple properties of convex functions that we'll actually end up needing. And so I pulled this from a collection of different sources, and I'll try to give you links to those in the description. And so this first one is coming from so the source for this one is coming from Marcus Grasmayer. I'm sorry if I mispronounced your name. I don't know who this guy is, but he put together a nice little intro to some properties of convex functions, and so we might as well go ahead and talk about it and leverage his expertise. So to start, we're taking a look at his proposition. All right, so what he says is assume that f, which goes from Rn to R, is differentiable. And generally speaking, what we need when we say that, it doesn't strictly mean this, but is that all the partial derivatives of f exist and they are continuous. You can still be differentiable without that, I think. Maybe? No, actually I don't think it can be. So yeah, that's what we got. Then we say, then f is, I'm actually only going to use half of this. Then if f is convex, so if f is convex, there we go, then for all x and y and Rn, we have this f of x, or f of y, is bigger than or equal to f of x plus gradient of f at x times y minus x. Now in his notes, he's choosing the gradient to be a column vector, but in my experience with engineering and other things, I've always found it more convenient to think of it as a row vector. So we'll stick to row vector notation, and I might cry and scream as I make mistakes, trying to keep that consistent. But it does look like it comes up very often. Something to note is that this ends up being a necessary and sufficient condition. So you can start with, say, this half, and you can get f as being convex out of it. I'm not going to bother with that because I actually don't need that for the next proof that I'm trying to demonstrate, which is the convergence of the gradient descent method, and just save some time. I'm just not going to go into it. But if you do want to see it, again, I'm going to link the notes that I'm seeing here, and you can go and look at that. It's only a few more lines past what I'm going to cover. So then if we take a look and we say that, so first we're going to assume, so we're going to let f be convex, and we're going to let x and y be in R, but assume that they're not the same points. And so by convexity, we get the following. So here we have f of x plus y over 2 is actually going to be less than or equal to 1/2 of f of x plus 1/2 of f of y. Now if you go back and you look at the definition of convex functions, I basically said that we choose this lambda, and by the way, I should say that lambda has to live in, say, 0, 1. And so basically we're just choosing lambda being 1/2, which then makes this 1/2, and that makes this 1/2, right? So, so then we have that. And so it's what we get. Now if we replace h with y minus x, then this becomes f of x plus h over 2 is less than or equal to 1/2 of f of x plus 1/2 of f of x plus h. What he's trying to do here is he's trying to set up a directional derivative. And so basically if you take h as it goes to 0, that's basically going to give you the gradient of f times h. Okay, so then what we can do is we can do some manipulations, and then what we get is this, just moving things around and multiplying. So we get f of x plus h minus f of x is then greater than or equal to f of x plus h over 2 minus f of x, and all divided by 1/2. Okay, and so now that gives us a general formula that we can start following. And yeah, so now what we're going to do is we're going to replace 1/2 with 1/4, then 1/8 or 1/16, and etc. Basically a sequence that's going to be going to 0. And then that's going to end up giving us a, and so that's going to give us a limit. So then what you can do then is this. So you repeat this same line, and so we can repeat this with x and x plus h over 2 in the place of x and x plus h. And then you get this. You get f of x plus h minus f of x is bigger than or equal to, say, f of x plus h over 2 minus f of x divided by 1/2. And this is bigger than f of x plus h over 4 minus f of x divided by 1/4, right? And so we keep that going, and then ultimately what do we get? We get f of x plus h minus f of x is bigger than or equal to f of x plus h divided by 2 to the k minus f of x divided by 1 over 2 to the k. And so this is, you can really see here how we're building up to the derivative. So basically what we're going to be doing is taking a look at the directional derivative. So we're going to just real quick just talk about a definition. We say that the directional derivative of f at the point x in the direction h is given as say df x semicolon h, and this is defined to be equal to the limit as t goes to 0 of 1 over t of f of x plus th minus f of x. And so then that's the definition, and it turns out this satisfies this, which is feels a lot more natural. So df of x semicolon h is equal to the gradient of f at x times h. Okay, so then what does that mean? Well, we have, if we basically put a lemma soup in here, what do we get? We get a f of x plus h minus f of x is bigger than or equal to the lim sup of k going to infinity, which basically means that this quantity is going to be bigger than every subsequence coming out of this guy. And so we get f of x plus h divided by 2 to the k minus f of x divided by 1 over 2 to the k. And so that is equal to df x semicolon h, because it's silly to talk about the supreme limit in here anyway. The limit exists. We know it's differentiable. And this is equal to the gradient of f at x times h. Okay, so putting that all together, what do we find? Well, we find that we have f of x plus h minus f of x is equal to the gradient of f at x times h, and now we know that h was equal to, well, let's take a look. It was equal to y minus x. So we go ahead and plug that in. We get f of y minus f of x. So we get less than or equal to here. It's bigger than or equal to the gradient of f at x times y minus x. And if you go and you look back at the beginning of the statement, this is exactly what we're trying to prove. So we'll just stop there. Now, like I said, you can use this to demonstrate that a function is actually convex, but I want to save a little bit of time for the other things that we want to talk about today. Okay, so great. So that is one of the so that's one of the properties that we're going to need of convex functions, and then the rest is really just going to come down to proving this convergence. Okay, so let's go ahead and start talking about the gradient descent method and convergence. So generally speaking, we're going to choose an x naught as an initial point, and this is in Rn, and we advance to the next point using this equation. So we have x of I plus 1 is equal to x of I minus some t times the gradient of f at xi. So we use the information at xi to direct us to where we're going next. And so we need to figure out what is this t. So how do we choose t? So this isn't an optimization class, but I did want to talk about this because it is going to come up later when we talk about some more approximation schemes and things like that. And so I didn't want to go too in-depth with this, but other things you could do is you could actually have this step size changing for each I, and people use a whole host of different methods of finding the correct step size for each given index. For our purposes, we're just going to keep it as constant, and this will end up working for us. But there could be better step sizes to choose. We're just not going to cover all of them. All right, so let's go ahead and talk about this convergence theorem. And this here, this is coming from another collection of notes, and this is by Ryan Tibshirani. I have no idea if I'm pronouncing that name right, but there you go. Hey guys, so what we're going to do is we're going to suppose that f going from Rn to R is convex. and differentiable. And that its gradient of f of x is Lipschitz continuous. If you don't know what that means, that basically means that there exists an L greater than 0 such that the gradient of f of x minus the gradient of f of y is going to be less than or equal to L times the norm between x and y. So that's what Lipschitz continuous means. Okay, and so with that, what we have is that if we execute the gradient descent method, with for k iterations, with a fixed step size t, which is going to be less than or equal to 1 divided by the Lipschitz constant, it will yield a solution which satisfies this. So basically we're going to have the kth step, so fk, minus f at x star, where that x star is going to be the minimum, is less than or equal to x naught minus x star squared, and then that divided by 2t times k. And so so then what we're seeing is that thus the gradient descent algorithm converges with order 0, 1, big O of 1 over k. And here note that f of x star is the minimum of f. Okay, so there we go. Okay, so basically, so we see that if we get this, if we arrest the rate of change of f itself with some sort of Lipschitz constant, and basically this means that the Hessian, or the second derivative of a several variable function, is bounded. Then we can take that bound, take its reciprocal, and as long as our step size is less than that, then what we have is that we have a convergence of our gradient descent method. So, so that's what we're going to be trying to prove here. Okay, so here we go. So the first thing we're going to do is we're going to expand f about the point x using Taylor expansions. Of several variables. So there's something that we should note, though, is basically we're going to have so we have f of x plus the gradient of f of x times y minus x plus 1/2 of the gradient of f squared at x times the magnitude of y minus x squared. And so they're basically declaring that this has to be bigger or equal to f of y. Now this is what they wrote in the notes, and they said we use a quadratic expansion, which really isn't necessary. If we do a linear expansion, basically what we're going to get is we're going to have something that's similar to that c that we saw before sitting in here. It's not exactly the same, but it's close enough. And so we can, so then basically what would happen is then, basically, this is equal to this, for some c, using something similar to the mean value theorem. Basically it is the mean value theorem. We just pick a line between x and y and we just treat that as a single variable function, and then later on you spit out some other things. But in this case then you'd have y minus x transpose on this side and y minus x on this side, and this is the Hessian, which is a matrix of all the second order partial derivatives of f. So anyway, so then what you would do is we can just go ahead and replace this first by the magnitude here, which will make this strictly larger. So that's going to be f of y is less than or equal to f of x plus the gradient of f of x times y minus x plus 1/2 of f squared. This matrix times y minus x squared, and so then this is going to be some matrix norm, which maybe you don't know what that is, but basically what we know is that this is going to be bounded by L. So so if you're willing to accept this, might make your day a little bit easier. I'm not going to ask you to prove this particular theorem on the exam, but I do want you to see it. So this is where we need to get to. So we use that Lipschitz constant to get us bigger than this, and yeah. So this is something that we're going to need. Okay. So now what we're going to do is we're going to replace y with the gradient descent update law, and so replace y with this, and so it's going to be x, we're just going to say plus, so being the next iterate, is equal to x minus t times the gradient of f of x. Okay, and so when we do that, what we get is this. So we get f of x plus is less than or equal to f of x plus the gradient of f at x times x plus minus x plus 1/2 of L times x plus minus x squared. All right, and then so just doing some manipulations and plugging in definition, you get down to this, and so this is going to be equal to f of x minus the gradient of f at x times t times the gradient of f of x transposed. Yeah, I guess this should be transposed up here too. If this is a row vector, then we want it to match a column vector, which is this. So I suppose back here, this should be transposed. But okay. So then that's what we get there, and let's see. Alright, and then we continue on and we get 1/2 L times the norm of t gradient of f of x squared. Okay, so since this is a row vector times a scalar times a column vector, we can move the scalar out, and so this is going to be a row vector times column vector, itself a scalar. So it's going to be f of x minus t times the norm, the gradient of f of x. Remember, f of x is a scalar valued function, but a multivariable function. So yeah, so we get this squared, so it's a scalar minus a scalar, and so we're happy with that so far, plus 1/2 L t squared of the norm of f of x squared. So keeping this going, say we can go ahead and write this as f of x minus 1 minus 1/2 L times t. This itself times t times the norm of f at x. So there we go. So we have f at the advanced point is going to be less than this. Well, one positive thing is that it looks like it's going to be less than f minus some positive quantity, because t is less than 1 over L, so that means that this whole quantity is less than 1/2, which means that this is positive, which means that this whole quantity is positive. So we are definitely decreasing from f going up to x, but now we want to see that it's decreasing in some cogent way that is going to give us convergence. So we're not just willy-nilly just sort of subtracting something positive. And so in particular, all my discussion that I just said with the comparison of t and L basically gives us this: f of x plus is going to be less than or equal to f of x minus 1/2 of t times the gradient, the norm of the gradient of f, and that quantity squared. Okay, and so this is positive unless this is 0, and if it's 0, we've already won. And so, basically, if this was 0, we wouldn't even proceed, and we would have actually found our optimal value. So then we'll just assume, so then we would have won. Okay, so now we need to go on and demonstrate that this is actually converging to what we want. Okay, so I'm going to label this guy with a star. All right, next is this. So if we take a look and at that proposition we mentioned earlier, we have this from convexity. So f of x is going to be less than or equal to f of x star plus the gradient of f of x times x minus x star. And this is by convexity. And so, then plugging this in a star, what do we get? So we have f of x plus, and so replacing f of x with this quantity on the right, we get this. We have f of x star plus the gradient of f of x times x minus x star minus t over 2 times the norm of the gradient of f of x. That's a mess. And that quantity squared. Okay, so now I can move over f of x star, and so we get f of x plus minus f of x star. And this is less or equal to, let's see. So if I pull out a 1 over 2t, then what I have left is this. So we put a 2t on the gradient of f of x times x minus x star, and then we subtract. So we took out 2t, so we get t squared, and that just ends up being t squared on the gradient, norm of the gradient of f. All right, and now I'm going to add and subtract something, and basically it's going to do something like complete a square. So we get f of x plus minus f of x star less than or equal to 1 over 2t times 2t gradient of f of x times x minus x star minus t squared norm of gradient of f of x squared plus norm of x minus x star minus norm of x minus x star squared. And you can see how this ends up being completely square. You can basically see if x minus x star times the gradient of f all on their own, then you have norm of f squared, and then you're going to have this guy squared. And over here we have 2t. So it's just like something like you'd have like a plus b quantity squared is equal to a squared plus 2ab plus b squared. But then the difference is when you start talking about multivariable functions, so vectors. So you have ab times a plus b is equal to, ends up being norm of a squared plus a transpose b plus b transpose a plus the norm of b squared. And since these are each scalars, those actually equal to the same thing. So you get 2. So we get norm of a squared plus 2a transpose b plus b squared, and so that's what we have there. So if I take this guy, and this guy, I can turn those guys as a perfect square. So moving these guys off to the side and out of the way, what we get is this. So this is less than or equal to, or well, in fact equal to 1 over 2t times, yeah, so we're going to have in brackets, we're going to have the gradient of f of x transpose plus x minus x star, and this quantity, well, transposed times f of x plus x minus x star, and this times x plus x star squared. Whew. Oh, and I need a t somewhere. So t looks like it's hanging out on the f. So you have a t. There we go. So then what we get is this. Let's change colors real quick so we don't run into all those guys. So this is equal to 1 over 2t times the norm of t gradient of f of x transposed plus x minus x star squared plus x minus x star squared. Right, so that's what that reads, how that reads. Okay, so oh, and there was a minus sign I missed in here. So since I had a minus sign on this guy and a minus sign on this guy, we were actually subtracting that. So that should be a minus there, should be a minus there. Okay, sorry for the confusion. Okay, so cool. So that gets us that. Okay, so what do we do next? Yeah, that's what it was. And looks like I missed another sign here. That should have been a minus sign. Yeah, because this was a positive. Right, there we go. All right, feel better now. Okay, so putting a minus sign here, and yeah, now that can be rewritten as x star minus x minus t gradient of f at x. All right, and so this is actually x plus. So what we have is this. We have this is equal to, well, might as well just rewrite everything. So we have f of x plus minus f of x star is less than or equal to 1 over 2t times the norm of x minus x star minus x plus minus x star, and these quantities squared. Okay, so that's getting us a lot closer, and we're almost done. Okay, so let's go ahead and wrap this up. So we've hit a really good spot right now, and yeah, so what we're going to be taking a look at is this. So we're going to consider a sequence of x0, x1, x2, etc., x all the way up to xk, where basically, you know, in place of x plus, we're looking at the actual member of the sequence. And so what we see is that if we take the average of these guys, f of x I minus f of x star. So I going from, say, 1 up to k, and then we divide by k. Then what we ultimately have is that this average is going to be bigger than the kth iterate minus f of x star. And the reason for that is that, that we already know that this is a decreasing sequence, and generally speaking, we have it somewhere in here. Yeah, here. So we know that if we go from xi to xi plus 1, then f evaluated at that point is going to be actually smaller. So that means that if we take the average of all of these, then the average has to be bigger than the smallest one, and the smallest one is the one that we have at the end. Okay, so so this is what we have, and this is in parentheses here, by the way. So then, what we can see is that this is less than or equal to 1 over k, and if you, we can go ahead and replace this with the sum 1 over 2t of absolute value of x minus x star minus x plus minus x star squared in each case, but instead of that we're going to have I minus 1, and we're going to have I. Right, so basically just copying this over but replacing it with the sequence terms. Okay, and again, I is going from 1 to k. And now you'll notice that this is actually a telescoping sum. So all that's going to be left is the first, or the endpoints. So it's going to be 1 over k times 1 over 2t times, it's going to be x0 minus x star squared minus x of k minus x star squared, and yeah, and so then we can go ahead and remove this piece and make things bigger. So it's going to be 1 over 2tk times x naught minus x star squared, and that's actually what we wanted to prove. So there we go. And so basically what we see is that the difference between the f of x sub k, which x of k comes from the kth iterate of our gradient descent algorithm, and the optimal point, this difference is being constrained by this. And so thus we have convergence. So that's a really handy sort of thing to have, and yeah. So I felt like I kind of botched this explanation here, so I want to go over that again and do that. If you keep hearing tire squeals, that's my wife playing Junkenstein's Revenge over in the other room, and apparently it's getting picked up by the mic. In any case, so I want to take this piece here. Well, we'll just take this piece here, and we'll talk about the and we'll talk about the completed square. So if that wasn't clear, maybe I can help clear it up a little bit more. Okay, so the idea is that we think this should be something like, for some vectors a and b, this should be, say, a minus b transpose with a minus b. And in fact, it should be maybe minus that. And so if you go ahead and expand this out, you're going to get a transpose a minus b transpose a minus a transpose b, and then plus b transpose b. And now for each of these, this is going to be a norm of a squared minus 2a transpose b, because both of these quantities are actually the same, and plus the norm of b squared. So we have the norm of one of these guys squared, and then we have some cross term here, but we don't have the other one. And so the other one would be this guy. And so so far we have a is equal to t squared norm. So sitting here in place for a squared is that we have t norm a gradient of f of x, right? So that's one term. And another term we need is this guy. And so so we want this term, norm of x minus x star squared. Okay. So if I add and subtract that to that term, so we're going to have 2t gradient of f of x times x minus x star. Now these are column vectors and this is a row vector, so it's going to be a little bit different than strictly this, but we'll see what as we go. So minus, say, we have t norm gradient of f of x. So we're going to have grad of f of x, that's a row vector, times grad of f transposed, right? So these, I'm thinking of each of these column vectors, and that's typically what you do. And so, but since f is a row vector, I need to be a little bit more cautious about it. Then I need to, say, subtract. Well, if I pull out a minus sign, actually, this will help here. And then I'm going to add, see, x minus x star transposed with x minus x star. All right, so since each of these are column vectors, I'm basically adding a row times a column. So again, this is scalar, so that's good. And this is norm of b squared. But if I add that, I need to subtract it, right? So I can get x minus x star transposed with x minus x star, right? Okay, so now this piece here ends up being something we can expand. And so on the inside, we end up getting t grad f of x transposed, and then subtracting x minus x star. And now this transposed against the same thing. Oops, not squared there. And then we finally have, using this piece, it's going to be minus, I'll just put norm of x minus x star squared. Right, and so then this here, so we have minus the norm of t grad f of x transposed minus x minus x star squared minus x minus x star squared. So hopefully that clears up any sort of confusion there. But that's basically how you do Completion square with vector quantities. Anyways, so I think that's all I wanted to talk about today. And so we have found a defined the gradient descent algorithm, and we proved that it converges as long as we have a convex objective. What we ended up finding was that if we pick our step size to be 1 less than 1 over L, where L is the Lipschitz constant of the gradient, then we're going to get convergence. And so there are other ways to choose step size, but just for like a one lecture sort of introduction to the gradient descent, this is a good place to stop. And then next we're going to get into initial value problems and coding, all this stuff. We're going to have several lectures for all that. Anyway, so thank you for hanging in there, and yeah, I'll see you next time. Hey, welcome back to Numerical Analysis. So I thought I'd get outside and record for a little bit. I just finished recording my intros for my tomography class, and so while I'm out here, I figured keep things interesting, and I'll do one for numerical analysis. So you can see this is my backyard, and we're right next to a nature preserve, so there's going to be quite a lot of noise. We actually get bobcats and other things roaming around here. I've seen deer out here a few times, a bunny, and raccoons. So I don't know. Maybe we'll have a visitor here and there as we go. Mainly, it just turns out to be loud birds, which is really annoying for recording. Anyway, we have thus far recorded up through doing lectures for it was Newton's method, I think, and I was going to do more on the secant method and a few other things, and maybe if there's time, I'll go back and do that. But in the interest of time and considering the other things we want to cover, so for instance, I want to talk about gradient descent, which is what we're talking about today. But then there's a few other things like initial value problems and whatnot. And then I want to sort of tie everything together with a project that actually I have published that sort of integrates everything all at once. But today what we want to talk about is the sort of optimization method. So the topic of these couple of lectures for like Newton's method and doing things with and what we're going to do with gradient descent method is basically sort of things you do with nonlinear functions. So for Newton's method, basically the idea was that we wanted to find the roots of nonlinear functions, and we use that by taking derivatives and linearizations and following those to zero and using that as sort of the next guess. And we saw there are some, if you start in a small region of where the actual answer is going to be, then you'll converge there. The gradient descent method is something that takes a look at a different kind of idea, and this is for finding maximums and minimums, gradient descent is for finding minimums of a function. You can flip it around and find maximums if you want. But in order to do this in sort of its full practicality, we need to talk about functions of several variables. The gradient is simply the derivative of a function of several variables, and so we're going to be taking a look at it in this light. So if you remember back from Calculus 3, we had the gradient of, say, a two-dimensional or even a three-dimensional function. And if you look at the level sets of that function, the gradient ends up being the direction of maximum increase. So if you follow that, then you're going to be increasing the most infinitesimally in that region. And so then they actually sit as sort of being orthogonal to our level sets. Now, the gradient descent basically means that you're going to be decreasing in the you're going to go in the direction of maximum decrease. And so the idea there is that if we want to find the minimum of a function, well, we should start at a point and then just start decreasing as fast as we can. And so this has led to a whole collection of optimization routines that basically operate this way. So if you are given, say, a collection of something that's like a function that you want to decrease as much as you can, say you want to find the minimum energy, or you want to find sort of a best fit for like a polynomial, and this is related to our polynomial derivative, our polynomial approximation stuff that we did before, then the idea is that you want to follow you want to take the gradient and you want to adjust your x from wherever you start to a point that you hope is going to be smaller by following the gradient down, the negative of the gradient. And so then you iterate this over and over again, just like with Newton's method, and then you hope that eventually you'll get at the smallest part. I'll go ahead and stop here, and then we can go ahead and we can talk about how all this works. All right, I'll see you on the other side.